Hey guys, welcome back, and in this video we will be talking about the equilibrium constants and the formulas used to find pH, to find concentration of acids, to find dissociation constants of, let's say, water. There are many things we're going to figure out, and there are different sorts of equilibrium constants to serve different purposes. So we're going to work through multiple calculations as well in this entire chapter. It should be interesting, and it should also teach you a lot in terms of the number of calculations you might need to do on your paper. Great. So equilibrium constants, the first thing I want to teach you guys is pH calculation. Very important. And this is a concept that a lot of people have been curious about for so long, from long before IGCSE till now. What really is pH? Because you guys were never taught this. So what is pH? How does it come? And let's look at the calculation. So what does the pH tell us first? Let's understand the objective of pH. It is a measure of how acidic or basic a solution, substance or chemical is. Either or anything. Okay? So we want to understand how acidic anything is. A pH of 0 to 7 is an acid, a pH of 7 is neutral, a pH of 7 to 14 is basic. And this is something that we have come to. These are numbers we have concluded to. It's sort of arbitrary, but not exactly. In the sense, it is giving you a measure of really what the pH is a measure of concentration of H plus. So all of these numbers that you have, 0 to 7, 7 and 7 to 14, these ranges have been figured out with respect to how in solutions around us we see the concentration of H plus. So the entire range of H plus concentration that can be physically sort of possible. I mean, it can also be beyond this range actually, but we just don't see it normally. So we just these range of H plus concentrations to several powers of 10, could be 0 concentration, could be several powers of 10 of concentration of H plus. All of these have been sort of brought into a small scale of 0 to 14. So it has, all of that has been squeezed into a 0 to 14 scale. So we use something called a logarithm to scale down such a big range into a linear scale of 0 to 14. Okay, and upon doing that, what we have is a linear scale which we divide into two equal parts, 0 to 7, which is acidic, and 7 to 14, which is basic. Now there's a reason it is like that. That's a bit of a different story, but it is always the entire conversation of pH comes from how much H plus ions there are, and based on that we understand or we figure out if it is acidic or basic. So let's look at more examples and you will see why 0 to 7, why 7 is neutral and 7 to 14 is basic, and how do we even come to this 0 to 14 scale, right? So that's the interesting part. To understand why we come to this 0 to 14 scale, we need to understand how pH is calculated. pH is calculated by the concentration of H plus, and we use a logarithm to find it. So pH is defined as the negative logarithm of base 10 of H plus ion concentration. So pH of any solution, let's say this is a solution and you have H plus ions and Cl minus ions. So you are finding the concentration of concentration of H plus in HCl solution. So in this case, what you're going to find is you're going to take the concentration of H plus, let's say 0.2 mole per dm cube. This is the concentration of H plus, and you plug that in over here, and you take the log 10 of that concentration, log base 10 of that concentration, and multiply with minus, and you find the pH. Do you want to see it work out once? Let's do that. Let's take this example of 0.2 actually log of, when you do log over here in the calculator, it automatically sets the base as 10. Okay, so log of what do we have? 0.2. What does that give you? That gives you a concentration, pH of minus 0.698. What a number. So minus times minus 0.698. Okay, so this is why you have a minus in front, because we don't want a negative value, and this minus basically cancels this minus, and at the end of the day you have a pH that is positive. So 0.698. Usually it is not less than 1, but sometimes it can be. Usually it ranges from 1 to 14. So 1 basically means 10 has a power of 1, and 14 basically means 10 has a power of 14. So these are the ranges of H plus concentration. What does base 10 mean? So whenever you have a concentration over here, let's say 10 to the power 5 concentration of acid, that means your pH will be 5, minus 5. Okay, so essentially all it is doing is it is giving you, by the way, minus 5 means extremely acidic, and that is a lot. That usually you don't find that. You can't really find that, I guess. Perhaps you can, I don't know. But let's take a more usual example, 10 to the power minus 5. Okay, in case of 10 to the power minus 5, the pH is going to be 5. So all it is it's finding the base 10 is basically giving you what is the power of 10 for which I can find the value inside. So at what power of 10 will I get 10 to the power minus 5? Minus 5. So similarly, if let's say I have 2 over here, 2 mole per dm cube, what is the power of 10 for which I get a value of 2? That would be log of 2. That is 0.3. Let's check it out. 10 to the power of 0.3. Do we get 2? Almost 1.995. So if I had to make it more accurate, 0.10299566. Okay, now it's almost 2, pretty much 2. So that is all it's doing. So the concentration, basically the reason it's 1 and between 1 and 14 is because the concentration of acid itself is going to range between 10 to the power minus 1 to 10 to the power of minus 14, where 10 to the power of minus 14 means very little acid, and that means very basic, and 10 to the power minus 1 means very acidic. Okay, usually this is the max we see, 10 to the power minus 1. That is why it's capped at pH of 1, but it can be negative. That is, your pH can be negative. If your pH is negative, that means the concentration of H plus is highly positive or positive. So it can be, let's say, 10 to the power of 2. That means your pH will be minus 2 according to this equation. But obviously there's a reason we have minus in front of the equation, and that is because we don't see such numbers, my friend. We don't see such high concentrations of H plus ions, which is why we have a minus in front, so that we only work with positive numbers. Okay, do we get the idea? Hopefully we do. So that's how pH is calculated. You take the concentration and minus log base 10 of that concentration. Why log? I just told you, log is used since otherwise the values are large and has a huge range. Log simplifies it and expresses all values as a power of 10. So even if you have a concentration of 10 to the power minus 14, or you have a concentration of 10 to the power minus 1, that's a huge range. That is 14 orders of 10 range. That's humongous. You can't express that in any linear scale. So you basically squeeze it down onto a linear scale by converting into a log scale. So what it does is it converts into log scale and it puts it from 1 to 14, where 1 to 14 is basically negative powers of 10. Sort of. Okay? Yeah, negative powers of 10, you could say. Not negative powers of 10, but negative times powers of 10. Why negative times powers of 10 is log 10 of whatever H plus is. So negative times whatever power of 10 gives me this concentration. That is what logarithm means if you have not studied in maths. Okay, so that's why I phrased it that way. Good. Now let's look at an example. How the formula is arrived. We'll look at it in buffer calculations, I guess. We'll look at it there. Okay, good. So I guess it has to we'll be talking about H2O over here. There's also dissociation constant Kw. You also see come up over there. You'll get an idea of why and how we get to it. Anyways, so hopefully by now you should understand how pH is calculated. How or who, which researcher came up with this idea, you don't need to know. I mean, you'll get to know sort of why it's like that. And you already know why it is like that, because you want to range down into a linear scale and make it smaller. But by now you should understand, if you have the concentration of H plus, how do you find the pH of that solution? This is the moral of the story you should have right now. Now, one example that we have is calculate the pH of HCl when the H plus concentration is 2 into 10 to the power minus 2 mole per dm cube. My bad that I don't have it written over here. But yeah, so the answer will be pH is going to be negative logarithm. Whenever you just write logarithm, I mean, I would at least assume that it's base 10. So it's fine, but write base 10. So Lg means log base 10, and log means you need to write what the base is. This is usually the norm. Doesn't necessarily mean it's always the norm. Norms are created by human beings, so better to write log base 10. So yeah, minus log base 10 of whatever the concentration of H plus is, and you will find the pH, and the pH is going to be 1.7. You just put this into the calculator. Calculators are allowed for your exam, so here's the answer. You can also find H plus concentration by making H plus a subject. So if you know the pH, you can find out what the concentration of H plus is. Let's say I give you the pH is 1.3. Can you find out? You should be able to find out. So let's say pH is equals to minus log base 10 of concentration of acid, my friend. So now, okay, so now I have 1.3 over here minus log base 10 of concentration of acid. Okay, now what I'm going to do is minus 0.3 multiply with minus 1 either side, log base 10 of concentration of acid. The reason I'm doing two brackets over here, because this feels much more legal to do mathematically. Third bracket for H plus means this is the concentration, and this is the mathematical operator for, these are brackets for the logarithm itself. That's why I'm writing two different brackets, which is the right thing to do, I would say. Anyways, then you can raise both sides to the power of 10. So 10 to the power minus 1.3 and 10 to the power of log base 10 of concentration of acid. And what it's going to do is 10 and log base 10 gets cancelled. And you might come at me shouting, what on earth does that mean? Let me give you an example. If you have log base 10 of 100, what is the answer? What power of 10 gives you 100? 2. 10 to the power 2 gives you 100. So the answer of log base 10 of 100 is 2. Do we get that? Now let's say I have 10 to the power of log base 10 of 100. What is log base 10 of 100? It is 2. 10 to the power 2. And what is 10 to the power 2? 100. Do you see where I'm going with this? Whenever you have the base matching, so whenever this and the base itself matches, it cancels each other off. And what you're ultimately left with is the term itself, the term inside the logarithm. And that is exactly what you see over here. Let me give you another example. So let's say 9 to the power of log base 9 of 81. What is log base 9 of 81? What power of 9 gives you 81? 2. 9 to the power 2 gives you 81. So 9, this I can write as 2, right? So 9 to the power 2, and again 9 to the power 2 is 81. So do you see what got cancelled? This 9 and this logarithm base 9 got cancelled, and what all you're left with is the term itself. So whenever your bases are matching over here, log base 10, this 10, or whatever the value over here is, and this term over here, on which the logarithm has been raised, whenever these two terms are matching, you can just cancel the logarithm. Okay, you can cancel the base over here and the logarithm over there, and all you're left with is the term. That is exactly what we're doing. This is in maths, but I'm explaining it to you so you guys know what you're doing. And yeah, so essentially we can cancel it off, and all you're left with is 10 to the power minus 1.3 is equals to concentration of H plus. So 10 to the power minus 1.3 should be whatever it is, I don't know. .05 mole per dm cube. Do we understand? Hopefully it makes a lot of sense. Oh, that's bright. Good. Can pH be negative? 100% it can be negative. If your H plus is positive concentration, so 1 mole per dm cube, any positive value, it is going to be negative. pH is going to be negative. As long as this is true, if H plus concentration is larger than 0, any value larger than 0, the pH is going to be negative. Understand that for pH to be 1, the concentration has to be 0.1, because 0.1 is 10 to the power of minus 1. So log base 10 of 10 to the power minus 1 is minus 1, and then in front of this you have another minus, because pH is equals to minus of log base 10 of 10 to the power minus 1, or whatever you have inside. So minus this minus 1, this minus multiplies with whatever the answer this gives, and this answer gives minus 1. So minus times minus is positive. So the pH of 1 means that your concentration of H plus can at max be 0.1 mole per dm cube. That is it. Okay. So in essence, your concentration of H plus can be more than 0.1 mole per dm cube as well, obviously, but usually you don't see that, which is why we see the range between 1 and 40. So again, if I take another example, that if what happens if pH is 0, how do we get 0? For it to be 0, then your term inside has to be 1. That is, your concentration of H plus needs to be 1 mole per dm cube. Okay, in that case, what is the power of 10 for which you get 1? 10 to the power 0 is 1. So your answer, your pH is 0. Okay, go through these yourself, you will understand it yourself. I'm pretty sure this is simple maths. If you've never done logarithms, then it's a bit of a sad sob story, but you'll figure it out. So yeah, if your H plus is, the concentration of H plus is anything greater than 1 mole per dm cube, it is definitely going to be, the pH is definitely going to be negative. What did I give us the range? If H plus concentration is greater than 0, okay, no, this is wrong. Obviously this is wrong. For, let's say, even 0.9 or 9 itself, 10 needs to have a negative power for, it needs to be a negative power for getting the term 9. So if that is true, your pH is still going to be positive. It is just going to be less than 1. Yeah. So yeah, the range is actually, it has to be greater than 1 mole per dm cube. So your concentration needs to be greater than 1 mole per dm cube for the pH to be negative. This is not right. So yeah, my point is, as your concentration is going from 0 to 1, or you want a pH of between 0 and 1, what you really do is pH of 1 is achieved at 0.1. Yeah. So concentration of 0.1 means, concentration of acid of 0.1 means you get a pH of 1. So let's say you want to get between less than 1 to 0. So to get to less than 1 to 0, what are you going to do? You increase the concentration. So you increase the concentration from 0.1 to, let's say, 0.2. So it has now decreased. right? So if you're going more towards 0, so as you go in terms of concentration more towards 1, you're reaching pH of 0. Okay, so 0.3 again less, 0.6 less, 0.7 less, 0.9, it has reached almost 0. Now 0.99999, it is almost 0. So this is what I wanted to demonstrate, that as your concentration of acid is increasing and let's say reaching 1 mole per dm cube, your pH is reaching 0. Now the moment the the concentration exceeds 1, if it's 1 it's 0, if it exceeds 1 even by 0.0001, your value is going to be negative. Yeah, your value is going to be negative. So yeah, I don't know why I explained that too much. I just regretted saying the wrong thing, that's why. But yeah, if you want a pH of negative, you go and increase the concentration more than 1. So it is possible, it's just that we don't see it naturally. Yeah, I just explained that saying a lot. Now the next constant we want to work with is the acidic dissociation constant. What is this? This is essentially a measure of how much weak acids dissociate in equilibrium. Now, the reason we don't really work with strong acids as much is whatever the concentration of strong acids is, usually it completely dissociates. That is why it's called a strong acid. Okay, so since that is true, we, in terms of equilibrium constants, we are mostly working with, let's say, in this case, weak acid. That's why the Ka constant, the acidic dissociation constant, we are only considering weak acid. So that's one question that I've had from some of our students. And why are we not considering strong acid? Because strong acids are strong acids because they dissociate completely. Okay. So it is an equilibrium constant for dissociation of acids at room temperature, room conditions, RTP. Why only weak acid? Just explained. So let's take this example where you have some sort of compound. So like HCl, could be HCl, H2SO4, could be anything, some sort of a compound which dissociates into an acid. That is, it could be the proton or it could be any form of acid which has the donating effect, and it breaks down into a salt. It could be sulfate, could be anything, Cl minus, could be anything. But the examples I've taken, Cl minus and H2SO4, is from strong acids, but that is in my mind, that's why I'm saying it. We're not working with strong acids, we're working with weak acids. So it could be methanoic acid, right? So it could break down into H plus and methanoate ion, so salt ion. So that is also possible. That's a weak acid. Okay, that's one example. Now, in this case, water A is, by the way, the salt part. Okay, the 8 part. Okay, so it can be anything. A can be anything, depending on what acid you're working with. Whatever weak acid you're working with. This is the weak acid. Okay. Now Ka, the dissociation constant, is equals to your product's concentration. So the acid concentration, H plus concentration, and your salt concentration, divided by your weak acid concentration in the reactant. And just to let you guys know that the concentration of reactant does not change much. It does not. It barely dissociates and forms very little of your products. Okay. Yes. So, and the concentration of H plus and the salt is equal. Okay, the concentration of H plus and salt is exactly equal, because however much of H plus HA broke down, the same amount of H plus got dissociated as compared to the salt or A minus. Okay, because if 1 mole of HA goes dissociating, then 1 mole of H plus is there, 1 mole of A minus is there. Simple. Let's take an example to visualize this. CH3COOH. Okay, CH3COOH and H2O, so ethanoic acid, and it breaks down, it forms H3O plus and CH3COO minus. Good. So at the end of the day, what you're left with is, the reason you're left with whatever you're left with is you can take certain things out of the equation that you don't need. What do you not need? In the entire example above, we're working with the acid, weak acid. We're working with the acid, that is the proton itself, and we're working with the salt. Nothing else affects our equation or dissociation. Wait, what? Dissociation constant. Nothing else affects it. We care about the initial acid concentration. We care about the number of protons that emitted or acids that are emitted, and we care about the amount of salt formed. Okay, so essentially the concentration of H3O, you can just cancel it off. What is the difference between these two? What is the difference between these two? 1H plus, right? So all we are worried really about is the H plus itself, the amount of H plus in the solution. We're not caring about anything else. Okay, we're not really caring about anything else. So all we're considering is the H plus aqueous and the CH3COOH, COO minus. So the ethanoid ion and the H plus, amount of H plus emitted. So just to let you guys know that the concentration of H3O minus or the H plus ions is equal to the salt ions. It is going to be exactly equal. Why? Because the H plus came from here. This is H plus, and the CH3COO minus came from here as well. So if 0.005 moles of ethanoic acid breaks down, then that means you have the same amount, 0.0005 of H plus ions and ethanoid ions. So it's an equal concentration. So all we're considering is H plus and CH3COO minus. Now, so what you consider is concentration of these two as the numerator divided by the denominator, which is the ethanoic acid, and you will find the dissociation constant. Why is it useful? This will help you find out the pH of acids. You can find out the pH of acids using these equations. You find out the concentration of H plus, and then you use the pH is minus log base 10 of concentration of H plus. So you can find out the pH of acids, weak acids. So what are the assumptions of Ka equilibrium, dissociation acid equilibrium constant? Since it is an aqueous solution, does the H2O dissociate to give H plus as well? That's a valid question. So is just using Ka to find H plus concentration enough? Because we are not considering the H2O to dissociate. We are considering the H plus only comes from your ethanoic acid, not from H2O. So is this assumption correct, my friend? And the answer is yes. The Ka equation is correct. The H plus being considered from only the ethanoic acid or the weak acid is valid. Why is it valid? Since the H2O produces negligible amounts of H plus during the dissociation process of H2O. It barely dissociates, right? So due to that, we are not considering that H2O is producing any any considerable amount of H plus which can affect the equilibrium constant. So we are not worried about that. So number one assumption is we assume H plus due to H2O dissociation is negligible. This is also why the concentration of H plus exactly equals to the salt. So concentration of H plus exactly equals to the ethanoid ion in our last example. Yeah, I just explained this. Often you will also see that on the numerator you have written H plus concentration squared divided by whatever the reactant or weak acid you had. Why does this happen? This happens only because your concentration of the salt and the acid is exactly equal. So if they're equal, that means I can just write it as A minus concentration whole square in the numerator. I can also write it as H plus square. The reason we often write H plus whole square is because we are worried about the H plus concentration. We don't care about the salt. But anyways, you can do either or. But do H plus, that is the standard. The other assumption is HA concentration before reaction and after reaction is the same, right? The reason this assumption is important is because we're considering that at equilibrium, the concentration we have of the reactant is whatever it was initially. So the equilibrium concentration is equal to the initial concentration of whatever reactant you have, which is why this assumption works. So essentially what we are taking of the concentration of the ethanoic acid is what there was in the beginning of the reaction. So since it doesn't really change, it's a valid assumption to make, because very little of the concentration of H plus is changing, is being produced by dissociation of the weak acid. That is why it's called a weak acid. Okay. So those are the few assumptions we have. They will often ask you questions along these lines, so you will have to be prepared and answer what assumptions we have made, why it's useful and all that. Okay, I've already flag posted those above here, 1 and 2. What is the significance of Ka value? A high Ka value means what? Means the numerator is a larger value, right? What is in the numerator? In the numerator has the acid concentration and salt concentration. So let's think of the acid. If the numerator is higher, that innately means both H plus and salt concentration is higher. So forget the salt for a moment and think about the acid. If H plus concentration is higher, that means it's more acidic, right? The equilibrium situation of the acid is more acidic. Okay, so that means a high value of Ka, for example 40 mole per dm cube, that's too high, but anyways, it indicates that the position of the equilibrium lies to the right. Okay, actually it's not too much because we're talking about Ka and not the concentration of H plus. This is the concentration of Ka, not concentration of Ka. dm cube, wait, let me think. So in this case, the units of Ka is going to be dm cube, cancel. Yeah, it should be dm cube in this case. In this specific case, in this case of ours, and usually as well, when you're talking about Ka, its unit should be mole per dm cube only, because you have one reactant and it produces two products. So essentially you have products by the reactants. So there are two products, so 2 mole per dm cube times mole per dm cube divided by mole per dm cube, one gets cancelled and you're left with 1. So the Ka so it's right, this is what I was confused about, so I want to cross check it in case I've written something wrong. But yeah, high value of Ka, dissociation constant of acid, means that it's more acidic, so it's more towards the right side, the equilibrium is more towards the right side. That means that the acid is very acidic and it produces a lot of H plus ions. Okay, now low value of Ka essentially means that the equilibrium lies more to the left and it's a weak acid, so it's closer to pH of 7. Okay, for example, this 1 into 10 to the power of minus 4 of Ka. Okay, this is a very small value, right? So this would mean that your H plus concentration is much lower, so it's more acidic, more basic comparatively, so it's closer to 7. Could also be higher than 7. I mean, if it's an acid solution dissociating, it won't be higher than 7, but yeah, so it's going to be closer to 7 essentially, not higher than 7. Right, so next question, is there an easier way to find if something is acidic? Why do I ask this question to you guys, or why do you ask this to me? The reason is, the way pH works is it is scaled between 1 to 14 and it's easier to understand. If looking at Ka, I don't know what to understand, I don't know what the reference point is, so we're basically trying to do a similar thing we do to pH. doing so we're doing a similar thing that we do to H plus concentration, and we're doing it to Ka in this case, or the dissociation constant. So we're taking the equilibrium constant and doing something similar that we do with H plus concentration in case of pH. Over here, what we'll do is we'll form a formula to find something called pKa. Okay, so what is pH? So pH is minus log of H plus. So pKa is completely similar and unoriginal, and it is minus log concentration, you can say, or the constant, not concentration, constant Ka. Okay, the constant Ka, and that is it. That is what your way of finding how acidic something is, using dissociation constant of acid. So this is only used mostly for weak acids, because you get to know the dissociation constant of weak acids, and then you find the pKa. And the pKa is, again, it's smaller scale, and you understand how acidic or basic something is. It works the same way as pH. So pKa minus log base 10 of Ka. Less positive, smaller means more negative value. So minus 1.6 is more acidic than 5. In pKa, you do get negative numbers, as far as I know. When you do calculations, you'll see. So in a pH scales, you don't really get that, but in pKa scales, you get that, as far as I know. You can you'll do calculations and you'll figure it out yourself. Now, why is it that lower pKa means more acidic? So yeah, it's pretty much the same logic I explained in case of the pH scales, that why a smaller value or more negative values are going to mean more acidic in nature, right? So higher concentration of H plus will mean more acidic, and whenever you have higher concentrations, it becomes a more negative value whenever you do the pH calculation. Minus log base 10 of concentration, you get a minus value whenever the H plus is extremely high in concentration. So again, same logic applies over here. Why does a lower pKa mean more acidic? Lower pKa means more negative or smaller value. Okay, so let's see. We can also prove it mathematically. So pKa is equal to minus log base 10 of Ka, and so when you make Ka the subject, you're basically raising this to the power of 10. So 10 to the power of minus pKa. Okay, so you can break this down as 1 by 10 to the power pKa. Okay, so if your pKa value is lower, that means your denominator essentially is lower. That would mean that the overall value of this fraction will increase, because denominator is going smaller. So 1 by 8 is going to be bigger than 1 by 16, right? Sorry, 1 by 8 is going to be, 1 by 8 is going to be bigger than 1 by 16, because 8 is a smaller number in the denominator compared to 16. So essentially, whenever the denominator goes down, your overall value goes up. You guys already know this. So if that is happening, if overall value goes up, your Ka goes up. So that's why your pKa, lower pKa, could be negative, could be just closer to 0, or could be less than 0, could be anything. Smaller or more negative essentially gives you a higher acidic nature. Yeah. Next thing is ionic product of water. How big is this thing, man? Okay. Yeah, ionic product of water. So this is another equilibrium constant, which is an interesting one, I find. This equilibrium constant basically gives you the dissociation of water at room conditions. So water does dissociate, but very little. We talked about it above that. Very little H plus is produced by H2O's dissociation, and dissociation of water basically means H2O forming OH minus and H plus ions. That is all it means. So if the dissociation is so small, what's the point of doing that, right? What's the point of finding something called Kw? We'll find out. We'll see the use case of it. We'll do a bunch of calculations and you'll see why it's useful. So Kw is called the ionic product of water, and its value at 298 Kelvin is 1 into 10 to the power of minus 14. So it's just a constant. If temperature changes, all the reaction constants that you see changes as well. All the reaction constants, Ka, Kc, Kw, Kpa, all of these, sorry, there's nothing called Kpa, pKa, but anyways, Ka, Kw and Kc, all of these reaction constants, equilibrium constants, will vary if temperature changes, if these conditions changes. So if your room conditions are changing, those equilibrium constants change as well. That's one thing you guys should remember. They can ask you a 1 mark or 2 mark question. Okay. Nonetheless, it's just given that at this temperature, 298 Kelvin, your Kw is 1 into 10 to the power of minus 14. What this means, I'm showing you. Don't worry. So let's look at the example equation. Your H2O can go and form H plus and OH minus ions, and then the reverse process is also there, where H plus and OH minus combines and forms H2O. So the equilibrium constant Kc for this, the Kc, not Kw, the Kc for this means whatever your products are, concentration multiplied divided by your concentration of reactants. So H plus concentration times OH concentration divided by H2O concentration. This is giving you the equilibrium constant, equilibrium concentration constant for this overall equation. So where does Kw come into play? The thing is, your H2O doesn't change. Again, why? Because very little H plus gets dissociated. So what you do is you take the H2O to the other side. You take H2O to the other side, and H2O times Kc, the concentration of H2O times Kc becomes the Kw. Okay, so that is why Kw is a constant. Do we get it? So this Kw is essentially giving you, this is how Kw is comes into play. This is how Kw, you get the value of Kw. And Kw essentially is the H plus produced by dissociation of water times the OH produced by the dissociation of water, the concentration of them multiplied. That is exactly what Kw is. Okay, and it has been figured out that the concentration of H plus and OH minus multiplied is 1 into, at equilibrium conditions, is going to be 1 into 10 to the power of minus 14. Okay, and that means obviously half of it is your, not half of it, but like root of it. Why did I say half? Yeah, root of it is going to be H plus, and the other root is going to be OH. So like, because H plus concentration and OH concentration is equal. Okay, is exactly equal. So whatever the concentration of this is also equal to the concentration of this. So the product of these two is giving you a value of 1 into 10 to the power minus 14. So the concentration of H plus or OH is 1 into 10 to the power of minus 7 and 1 into 10 to the power of minus 7. Let's see if this makes sense. Multiply these two values and you will get 1 into 10 to the power of minus 14. So this is the concentration of H plus, this is the concentration of OH minus. And if you multiply that, you get the Kw. Okay, so this is why your pH is 7. neutrality is at 7, because we considered our reference point is actually that water is neutral. Okay, is there a concentration of acid, H plus in water as well, in just water dissociating? So take a glass of water. This is not a good example, it has coffee in it, but anyways, a glass of water, it has acid concentration as well, H plus concentration as well, but we just take H2O as a neutral element. Okay, we decided that is on us, and that is why 7 is your neutral reference point, because minus log base 10 of 1 into 10 to the power of minus 7 is 7. Okay, so this is why the 1 to 14 scale happens. I told you guys I will tell you later, and this is what I want to tell you, and this is also what I meant when I said when you guys get to ionic product of water, you'll understand what I'm talking about. Why the 1 to 14 scale exists. So that is pretty much the story of KW. Why is it useful? You'll ask me. What is this useless thing that you're studying? You'll see the use case of it when you do calculations. For now, understand this equation, that KW is actually nothing but the equilibrium concentration constant of H2O dissociation reaction. Okay? So your H2O dissociation reaction, reversible reaction, that equilibrium constant equation, whenever you take the denominator to the other side, or you multiply both sides with the denominator value or the reactant value or the H2O concentration value, you get something called KW. That's it. Now, why are we not taking H2O in KW? Because Kc absorbed H2O concentration. That's one way to think of it. The other way to think of it is it's simply that it has too much H2O, and changing the concentration of water does not change the KW. The reason being, if I just want to explain it using a number, I'll explain it using a number. 0.1 times 0.1 divided by 1 into 10 to the power of 7. Okay, let's take this example and let's find what the answer for this is. 0.1 times 0.1 divided by 1 into 10 to the power of 7. Answer is some 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Yeah, makes sense. 9. So 1 into 10 to the power of 9. Now let's increase this marginally. 1.1. What is this expression? This is okay. Interesting. Yeah, this seems a bit better. Again, this is supposed to be around the same value. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So my entire point is your value itself does not change much. Okay. Your overall concentration constant does not change much whenever your denominator is extremely large compared to your numerators. So let's take an even larger example. I don't know what this is even doing. So yeah, you have this example, and why is it giving me 100? Can you not just give me like 10 to the power minus 14? I'm so confused. Why is it giving me this? Anyways, so let me increase it by 0.1. Okay, not much has changed. It's in the same order of value. It's still 10 to the power of minus 16. Technically 10 to the power minus 14. But yeah, very little has changed in terms of the value itself. Percentage wise, the value has changed very little. So essentially, when you have such a large value compared to your numerators, the change in your denominator, it goes both way. It could be numerator, denominator, it doesn't matter. In this case, your H2O concentration is in the denominator. So changing anything of H2O is not really changing anything about the Kw. The Kw is relatively the same. Okay, percentage wise, there's not much of any change in Kw. So that is why we're only dealing with your H plus concentration and OH minus concentration, and that is what exists in your pure water. Okay, so good. Yep. Why did I repeat it again over here? But yeah, so basically Kc absorbs H2O concentration and you form Kw. Okay. So the product of H plus concentration and OH concentration gives you the Kw, and it is 1 into 10 to the power minus 14 in case of room conditions. Good. We can also further simplify this by saying since the H plus concentration and OH concentration is exactly the same, you can just write it in terms of H plus concentration squared. Okay, Kw is H plus concentration squared. That is also something you can say. Now what happens in case of pH of strong acids? Right? Now to find pH in any case, you need the concentration of acids, right? So in case of strong acids, the concentration of acid is the concentration of H plus itself, since strong acids completely dissociate. So whatever the concentration of, let's say, HCl is also the concentration of H plus ions in that solution. Okay. So if the concentration of HCl is 2 into 10 to the power minus 3, the concentration of H plus is going to be 2 into 10 to the power minus 3 mole per dm cube as well. I'm supposed to get a notification, that's why I paused. Am I getting it? Probably not. Hopefully not. Okay, so if the concentration of H2SO4 is 2 into 10 to the power minus 3 mole per dm cube, the concentration of H plus is going to be twice as that, because for every mole of H2SO4 you have 2 moles of H plus ion to be given off. So it's 2 times 2 into 10 to the power minus 3, which is 4 times 10 to the power minus 3 mole per dm cube. So after getting the H plus concentration, we can use pH is equals to minus log concentration of H plus to get the pH of that strong acid. Obviously strong acids also have variation, so I mean different H plus different strong acids will have slightly differing pH for the same concentration of itself, but that is because how much of the H plus dissociates. Okay, but yeah, in this case, in our cases, all we're doing is if there is 1 mole of H2SO4, there's 2 moles of H plus ions. Simple equation, simple conversation. If there's 1 mole of HCl, there's 1 mole of H plus concentration. Okay, I'm just trying to check if I'm even supposed to teach these stuff in this same video. Let me check. Where is it? No, okay. Oh, what am I teaching you guys? Buffer, equilibrium. It's still equilibrium constant, right? Damn, it's big. Yeah, buffer is the next one. Quite shocked to see that one chapter I've kept as this big. Anyways. pH for strong acids, hopefully you understand. pH for strong alkalis is the same story. So let's say strong alkalis fully dissociate as well. Whatever the concentration of alkali is also the concentration of OH ions. So concentration will be the same. If you have 1 mole of NaOH, the concentration of OH will be 1 mole as well. If the concentration is 2 into 10 to the power minus 3 mole per dm cube, it is going to be 2 into 10 to the power minus 3 for OH as well. So after you get that, right, after those value you get, let's say it is given to you that you have 2 into 10 to the power minus 3 mole per dm cube of NaOH. Now you can use the good old KW formula, dissociation of water formula, ionic product formula, and use that to find the concentration of H plus ions. Okay, using the ionic product formula, what you do is, if you know the OH concentration, you can find the H plus concentration. Okay, so that's the beauty of using that equation. So granted, this is given to you, NaOH, you find the OH concentration, which is exactly the same in this case, and you use the KW formula. So KW is equals to OH minus concentration times H plus concentration. So now you make H plus the subject, okay, and you know the KW value. The KW value, what has happened? Yeah, the KW value is 1 into 10 to the power minus 14. Wait, my thing needs charge. Oh, okay, this is, I can't charge. Okay. Anyways, so your KW value you know, which is 1 into 10 to the power minus 14, and your OH concentration, it is given to you 2 into 10 to the power minus 3. So you divide both of them to get the H plus concentration. Okay, so you divide both of them to get the H plus concentration, and H plus concentration is 5 into 10 to the power minus 12. And now you use the pH equation to find your pH value, which is minus log base 10 of 5 into 10 to the power minus 12, 5 into 10 to the power of minus 12, and you will get the pH of 11.3. Now, here's the thing. You will ask me a few questions. One question is, did I not just say that OH and H plus concentration is going to be the same, so you can use like H plus concentration whole squared? That is only when H2O itself is the only substance that is dissociating into H plus and OH minus. So this is only true if H2 is the only thing that is dissociating. It is not true when you have other systems where there are OH concentrations or H plus concentrations from other substances. Then obviously the H plus or OH concentration is going to be different. It's not going to be the same. That's number one. Thing number one. Thing number two is how on earth did H plus ions come into this solution? See, every solution means there's water in it. Okay, that is the beauty of KW, the ionic product of water equation. Every solution of base, of acid, it has water in it. It is aqueous. It is dissolved in water. And we know the ionic product value of water. It is 1 into 10 to the power minus 14. So essentially what that means is H2O is equals to H plus plus OH minus concentration. This equilibrium of, the equilibrium basically being KW is equals to 1 into 10 to the power of minus 14. Basically the concentration, the product of H plus concentration and OH concentration should always remain 1 into 10 to the power minus 14, my friend. That has to always be true. In an aqueous solution, whenever the water is present, the KW value needs to be 1 into 10 to the power minus 14. You have to paste that in your brain. And if that is true, if your H plus concentration or OH concentration is higher, the H plus concentration has to compensate and be lower. This is where the real game is. This is where the real fundamental lies. Your KW value is constant. It's a reaction constant. It's a equilibrium constant. And for this to stick, for this to remain true, if OH goes higher, your H plus goes down. Okay? So H plus concentration goes down in the solution. And that is why the H plus concentration is decreasing, because OH has increased. You have put in a lot of OH because you have put in NaOH. So To compensate for that, H plus goes down to restore the equilibrium. Le Chatelier's principle. I don't know, I've butchered the name, but like it's written over here somewhere. Where have I? Le Chatelier's principle. And it talks about restoring the equilibrium. You studied it before. So that is the important part over here. People get confused why KW is used. How does it make sense? Why is OH changing H plus, and why is 1 into 10 to the power of minus 14 being used? It's simple. KW needs to remain constant in any aqueous solution. If that needs to be constant, that means the product of H plus and OH needs to be constant, right? So if H plus goes up, OH needs to go down, or either or. If OH goes down, H plus goes up. I guess I said the same thing, but anyways, you get the idea. Now, what else? This is exactly what I just explained. Again, this is also what I just explained. Okay, good. Now, the other thing is you can also find pH by using the OH concentration. You don't need to worry about H plus concentration. Over here, we found out the H plus concentration and then use the pH formula to find the pH. You can also find something called POH, which is interesting. POH is basically the same formula with concentration of OH inside. Okay, it's the same formula with concentration of OH inside. So what do? We take the OH concentration and find the log base 10 of that concentration, and you will get something called POH. And you subtract that value, whatever POH is, from 14. 14 minus POH, and that is going to give you the pH. It's very interesting. It may be a bit trippy, but it works. You can check it out yourself. Do you want me to check it out? Yeah, sure, I will check it out for you. So if where is OH concentration? 2 into 10 to the power minus 3. So minus log base 10 of 2 into 10 to the power of minus 3. This is giving me 2.698. So 14 minus POH is supposed to give me pH. Yeah, there you go, 11.3. Is pH 11.3? Yes, it is. So this is a very basic solution. Okay, this is a very basic solution. Alkaline solution, not basic, alkaline solution. Yeah, I'm going to continue with the examples. Alright, now let's continue with some of the examples. One will be finding a pH, and we're going to essentially come to this value. So we're going to use what is the KW, which we've done above, and using the dissociation constant for water, we're going to come to the pH value. Okay, so that's the entire thing. So the question is calculate the pH of 0.1 mole per dm cube of NaOH solution. Again, similar question. So you know the KW to be 1 into 10 to the power of minus 14. Okay, so you write KW as 1 into 10 to the power minus 14. H plus you don't know, OH you know. Okay, so again, to keep the constant same, H plus will vary and compensate for however the OH concentration has changed. In this case, it has increased. So H plus concentration goes down, so it decreases. So now you will have the H plus concentration as 1 into 10 to the power minus 13, and the pH will be simply 13. You don't even need to put it in, because by seeing the power you can just tell. So yeah, the pH is going to be 13, which makes sense because OH concentration has increased a lot. So the H plus concentration will compensate by decreasing in amount. So if it's less acid in the solution, that means it's much more basic. So yeah, you have pH of 13. Another example. This is a bit more like examples that can come on my paper. pH of solution when 50 cm cube of 0.1 mole per dm cube NaOH solution has mixed with 50 cm cube of 0.1 mole per dm cube of H2SO4. So we want to find a pH of a solution where you have 0.05 dm cube. I always convert to dm cube, by the way. Yeah, 0.05 dm cube of 0.1 m by d of NaOH. Okay, plus you have in the solution H2SO4, yeah, H2SO4 of again 0.05 dm cube of 0.1 mole per dm cube. And what is the pH of this? So reaction will take place. Let me tell you what happens. The NaOH will react with H2SO4, and it will obviously form a salt and water. In the typical acid plus base reaction, it will form a salt and water, and it will also have excess of NaOH and excess of H2SO4. Sorry, either excess of NaOH or excess of H2SO4, not both obviously. One of them will be the limiting reactant. You have read this in IGCSE, in AS hopefully as well. So one of them will limit the reaction. Okay, so one of them will be less in comparison in ratio terms. So that will make sure that either the OH is left over or the H plus ions are left over, based on, you know, if the base or acid is left, was extra. Now whatever is left off essentially dissociates completely and causes whatever the pH is. Okay, so that is from where we get the pH. In general, if both of them were in right proportions, then your reaction pH would be exactly 7, because it's neutral. It's a salt and it's water. It would be neutral. Okay. Again, H plus comes from water. Acid only, not water. Okay. So let's do the calculation. It's a fun calculation. It's a good calculation. Let's see. First, we find the moles of H2SO4, my friend. The moles of H2SO4 will be whatever the mole per dm cube concentration is times the volume of it, right? So it is going to be 5 into 10 to the power of minus 3, because what is 5 into 10 to the power minus 3? 50 cm cube. We convert it into, give me a moment. Yeah, 5 into 10 to the power minus 3. That is going to be the volume. Correct? Is it? No, it's not. So yeah, I mean, it is wrong. So I've changed a few of the numbers. It should be from minus 3. It was written from minus 3, so it's going to be minus 2. Because obviously it's written 50 cm cube, so if you convert to dm cube, it should be 0.05 dm cube. And if you're writing a 0.05 dm cube as in standard format, then you're going to write it as 5 into 10 to the power minus 2. I don't know why I'm writing it this way in tens power format. I don't know, but like, sure. I've corrected the few places. So yeah, you're basically trying to find the pH of the solution, and in doing so, all you're doing is you are finding the moles of the acid that there is. You're finding the moles of NaOH that there is. You're finding how much mole of both acid and base gets used up, and whatever is left is contributing to the acidity or alkaline nature of the solution. Okay, so you find however much H plus is left now, after, you know, seeing that whatever gets used up gets turned into the salt and water. So yeah, let's see how much of moles of H2SO4 we have. So for H2SO4, we have 0.1 mole per dm cube of H2SO4 times 5 into 10 to the power minus 2. That is the volume of it. And then you have 5 into 10 to the power minus 3 moles of H2SO4. Moles for NaOH is the same because it's the same number. Okay, same number of concentration and volume. Now, what is the ratio? Ratio is 2:1. What does this mean? So for every 2 moles of NaOH, it is reacting with 1 mole of SO4. So what that essentially means is the sulfate is going, for one of the, every time 1 mole is being used up, or not 1 mole, but the ratio is set up in a way that you need half the amount of H2SO4 compared to NaOH, right? So that would essentially mean that probably, I don't know, H2SO4 runs out faster, or less of it is needed. Okay, not runs out faster, but less of it is needed compared to NaOH. So we're going to see that in calculation as well. For 5 into 10 to the power minus 3 mole of NaOH to react, I would need half as much of H2SO4. Why? Because for 2 moles of this, 2 proportions of this, I need 1 proportion of the sulfate. Okay. Reason being, over here you have 2 Na reacting with 1 SO4. So basically the Na in general will run out faster. More NAs are being used compared to your SO4, right? Compared to your sulfate. So half as much H2SO4 is needed in terms of concentration. So if you need 5 into 10 to the power, in terms of moles, if you need 5 into 10 to the power minus 3 moles of NaOH, you need 2.5 into 10 to the power of minus 4, not minus 4, I forgot to correct this, minus 3 moles of H2SO4. Okay, good. Moles of H2SO4 left is going to be the difference between however much H2SO4 there was and how much H2SO4 is needed to convert all of the NaOH, that is, convert all of the NAs to Na2SO4. Okay, so to use up all the sodium ions, we only need 2.5 into 10 to the power minus 3, not 4, 3 moles. Okay, so now we do the subtraction, and you're left with an excess of 2.5 into 10 to the power minus 3 moles of H2SO4. So 1 H2SO4 is releasing 2 H plus ions and 1 sulfate ion. So essentially you have a concentration of H plus of 2 times 2.5 into 10 to the power minus 3. So 5 into 10 to the power minus 3 moles. This is correct, right? Yeah, this is correct. So yeah, now find the concentration of H plus. The total, the concentration of H plus will be moles of H plus divided by the volume in which it exists. So the total volume is going to be volume of the reactant sort of left, and the volume of your products, right? So that is basically your entire aqueous volume. Okay, and you can directly find that from your initial reactant volumes, because nothing else added volume of water. Okay, nothing else added the volume to solution. It is the initial liquids, initial aqueous solutions that created the volume, and the volume didn't change. It won't. It's the same solution. Do you see, after let's say 25 cm cube of HCl, 25 cm cube of I don't know, NaOH, do you ever see the amount of liquid change from 50 cm cube? No. 25 added, the total solution is 50, remains 50. So yeah, it's the same case over here. You take the moles, 5 into 10 to the power minus 4 divided by the volume. So you have 50 cm cube of NaOH. What is it? I have to check upstairs. NaOH, 50 cm cube of NaOH and 50 cm cube of H2SO4. Okay, and divide by 1000 basically to convert to dm cube. Okay, so essentially you have not 4, 3. Yeah, so 5 into 10 to the power minus 3 divided by 0.1. So this should essentially give you, I believe, yeah, 1 by 200. Is it 1 by 200? Let's check. Let's use a good old calculator over here. I mean, this should be wrong. The answer should be wrong, by the way, because we considered 5 into 10 to the power minus 4 in the calculations. 5 into 10 to the power minus 3 divided by 0.1. It should be 0.05. 1 by 20. So it's 1 by 200 over here. It should be 1 by 20. Correct. Okay. 1 by 20. it was one more 0 because we were considering 10 to the power minus 4. Anyways, so now you know the concentration of H plus. So how do you find the pH? You find the pH very simply. You know the formula by now. pH is going to be minus log base 10 of 1 by 20. And there you go. You have it. You find the solution of this and it's going to be 2.3. So it's a very acidic solution because a lot of H2SO4 is left. Half of H2SO4 is left. Okay? That's one example. Another example let's take, my friend. Calculate the Ka of methanoic acid solution of concentration of 0.01 mole per dm cube. So dissociation constant we are going to find out of methanoic acid. Again, weak acid, we find dissociation constant of acid. Okay, it has 0.01 mole per dm cube and the pH of the solution is 2.19. Great. So first thing you always do is write the equation. HCOOH will break down into forming H plus ions and HCOO minus ions. So the pH of this is going to be, of course, minus log base 10 of H plus concentration. Okay, so you know what we first want to find out is we want to find out the H plus concentration. You want to find out the H plus concentration because the pH is already given to us. So if you want to find the Ka, what do we need? What is the end objective? Ka, right? For the Ka, I need H plus concentration. And I mean, if you know the H plus concentration, you already know COO, HCOO concentration as well. Both are going to be equal. H plus and this concentration, it will be equal, divided by HCOOH. Okay? And you know the concentration of HCOOH. So if you know that, if you know this, and you know this, all you need is either or, because both are equal. So I can write it as square. I have showed this why we can do that, because the equal concentration of the acid and the salt part exists. Okay, when it dissociates, if 1 mole dissociates, this 1 mole of acid, 1 mole of the salt part. Okay, good. So if we have these two, we are trying to find out the H plus using the pH formula. So the pH is giving us, we know the pH is 2.9. I have basically multiplied with minus on either side, and I have minus 2.9 over here, and log base 10 of H plus concentration. You take, you raise either side to the power of 10, okay, to the base of 10, and 10 to the power minus 2.9 is going to give you 1.259 into 10 to the power of minus 3. This is the H plus concentration. Again, 10 to the power of log base 10 gets cancelled off. I've explained this above, so revisit that. And this is your concentration of H plus after being dissociated. Okay, so in equilibrium position, the Ka is going to be 10 to the power minus 2.9, which is this value, whole square, divided by concentration of methanoic acid. Okay, now the methanoic acid concentration does not change much, and even if it does change, it doesn't change the Ka much, because its denominator is so much larger than your numerator that it barely affects the constant. It's at 0.01, and you find the answer, and the Ka happens to be 0.1259. This is your Ka. This is another example. Great. Next example, pH of 0.1 dm cube of 1 mole per dm cube of CH3COOH and what have I written over here? And 0.05 cm cube, I believe, and 1 mole per dm cube of NaOH solution. Okay. pH of 0.1 dm cube and 1 mole per dm cube of CH3COOH, and I have 0.05 cm cube. I'll convert that to, I guess it's dm cube. Yeah, I'll just write it as dm cube. 0.05 dm cube and 1 mole per dm cube of NaOH solution. Okay, so this is an interesting example, and for this I'll give you a hint. I want you guys to practice, try this on your own, and I want you guys to give me the answer in the comments if you guys can. So over here what you have to do is, again, you form or you write the reaction. Oh, I have already written it, so it's easier. Yeah, so you write the reaction out first and you find the products. The product is a simple H relation. It's going to form water and salt, right? So you remove the H and you put in the Na, and you form the salt and you form water. Simple conversation. Now the entirety of this is that what is the pH of this? Okay, what is the pH of this? How do you find the pH of this? First you need to find out how much of the NaOH, for one thing, more information sort of needs to be, I guess, given. But if you consider that all of the NaOH sort of gets used up, right? All of the NaOH gets used up. In that case, what is the pH of the solution? Okay, so all of the NaOH gets used up. What is the pH of the solution? Is the volume different? Yeah, the volume is different. So you will have some of the CH3COOH left, and due to having some of this left, the solution overall will be acidic in nature. Note that this is 1-to-1 ratio. So if all the NaOH gets used up, some of the acid is left. And you also need something, I guess you also need the dissociation constant. I believe so. Yeah, you do. You do need the dissociation constant. So you will then, once the reaction is complete, you work with the left off acid. So that is probably going to be around, I believe, 0.05 dm cube. And with that, you're going to find the pH. So that is the acid left, and that is going to dissociate and create the pH of the solution. So that is going to be, and let me make a dissociation constant for you guys. Ka for CH3COOH is going to be, let's say, what did we do in the previous case? 0.2. Let's make it 0.3. So I've given you the Ka is 0.3. Now you do the problem and tell me what the pH is below. You just comment it out. Okay, it should be easy. I've already explained how to do it. You know the Ka, you find H plus and you find pH. Simple. Okay, again you work with the left of acid. Okay, left of weak acid, not the entirety of the weak acid, because some gets used up into making the salt. Okay, great. Next is buffer solution. Finally, it's done. Okay, see you in the next video.